Hello, everyone. I'm Hongyi Li. Welcome to the lecture of MLSS 2021. It is my pleasure to introduce today's speaker, Dr. Karteek Alahari. Dr. Alahari is a senior researcher at the INRIA in France. He is based in the TOAD research team at the INRIA Grenoble, Rome, Elbe Center. He was previously a postdoc in the INRIA Willow team at the Department of Computer Science in ENS after completing his PhD in 2010 in the UK. His currently research focus on addressing the visual understanding problem in the context of large-scale dataset. In particular, he works on learning robust and effective visual representation when only partially supervised data is available. This includes frameworks such as incremental learning, weakly supervised learning, adversarial learning, etc. Dr. Alahari's work has been funded by Google Research Award, the French National Research Agency, and other industrial grants, including Facebook, Never Let Europe, Value. He co-organized an excellent tutorial on annotation efficient learning at CVPR 2020, and he has a great talk about incremental learning in the tutorial. This is why we invited him to MLSS. It is our great pleasure that he will talk about continual visual learning at MLSS. Please join me to welcome Dr. Alahari. Dr. Alahari, now the stage is yours.
Brilliant. Thank you, Professor Lee, and all the organizers for inviting me to this wonderful summer school. And it's sad that I can't present this to you in person, but hopefully, this medium does give us a chance to discuss. So what I'm going to do is, talk to you about this topic of continual visual learning. But what I would also like to mention is that, feel free to ask questions at any point. And I hear there are several moderators who will be transferring the questions to me by text, and I'll take them as and when they are relevant for the discussion, either immediately or maybe slightly later. So I do apologize for turning my head here and there because I have two screens where I do keep an eye on the questions, and hopefully I'll take them as and when they're relevant. So we're going to be looking at this topic of continual visual learning, but just before we go into the technical aspects, I just wanted to say a few words about the research center that I come from and where exactly it is, etc. So INRIA is a French national research organization which has about 8 centers all over the country, and I'm based in the one in the sort of southeast of France, which is Grenoble, in the middle of the French Alps. And I've been based here for almost 8-9 years now. So just to show a few photos of what the center looks like. So this is where we are based. Right now I'm actually working from home, but this is a center that where we usually work, which is sort of like a spaceship kind of building. So it's pretty futuristic, even though it was built over 25 years ago now, actually. And Grenoble being the center of the French Alps, or the capital of the French Alps, you do get amazing views over the mountains. And this is one particular photo that I picked online from some point in the fall, I think one of the years. And this is sort of a panoramic view of the city from a hill that is right in the middle of the city, which you can walk up to. Anyway, just to show off a few visual aspects of the city that I am currently in. So after that, I'm going to be talking about this topic on continual learning, more specifically continual visual learning, which means I'll be applying this idea of continual learning to computer vision problems. So we'll see, examples as we move along in this lecture. But before that, I just also wanted to mention that this word or phrase of continual learning has been called with several different names, such as incremental learning, lifelong learning, sequential learning, never-ending learning. So these are all sort of interchangeably used in the literature in the past 10-15 years. So when I'm mentioning continual learning, I could be sometimes interchanging this with incremental learning or lifelong learning, but they all pretty much mean roughly the same thing, but maybe very slight variations in a few cases. But we can say that for this lecture, continual learning, incremental learning, and lifelong learning refer to the same thing. Okay, so I thought I'll take a visual example from my own childhood, where we have a continual learning scenario, or at least I grew up with one. Where growing up in India, where I'm from, I was given breads which are called chapatis or rotis of this type, right? And they were wonderful, and then I grew up eating many of them, and I continue to eat. But as I continued to move around the world and start traveling, then my idea of bread had to be adapted. So then when I settled down in France, I was encountering breads of this form, which has nothing to do with the other one visually. The ingredients might be similar. The final result might be the same of having a carbohydrate side of your meal, but the actual form of it looks very, very different. So I did adapt or continually learn to this new scenario of an important food item, but I still, remembered which is potentially or can be called as the best bread from my perspective. So the first question, what precisely is the difference between continual learning and online learning? It's a very good question. We'll see that in just a little bit where I show you a sort of a spectrum of all different types of learning mechanisms. Okay, so we'll come to that. So here is a slide actually, courtesy of Professor Lee, who kindly introduced me earlier, where the idea of continual learning is basically you start with learning a particular task one, and you master this task with various forms. Let's say it is a supervised learning scheme. We have some training data, and then we use all the training data to master and solve this particular task. Now we move on to a new learning task, which could be, let's say, starting with task one, could be recognizing or classifying images containing, let's say, cows and dogs and different types of animals. Learning with task two could be actually segmenting all these objects that have been classified in the images. So now, given a new set of training data, I can now master both of them and say that you can actually solve both the new task two and also the previous task that you have already learned, and so on. And the hope is that by moving on from one task to another, you would finally get a machine which is pretty robust and intelligent, let's say, but hopefully not as scary looking as this one. But anyway, we are far, far away from this scenario. But the idea is that we do this in a continual and incremental fashion. So just to briefly recap on what exactly we do today in standard machine learning. I know you've had several lectures over the last 2 or 3 weeks, but just a few seconds to kind of take a look at or do a quick recap on the standard machine learning framework that you're already familiar with. So here we have a scenario where the entire data set is split into 3 distinct parts, such as the training data, the validation data, and the test data. Okay, and the main assumption that we make in this particular scenario is that all of this data are sampled from the same distribution, which means that your test and the training distribution, data distributions are one and the same. This is very important because when you train on something, you would like to be able to generalize to test, but you do make the assumption that the data is from the same distribution. Now, given this scenario, we have made excellent progress over the last 30, 40, maybe even 50 years, where what we are now able to do, thanks to all this progress, is we can solve several tasks on benchmarks and what we can call as academic data sets. So this is a task that is fairly well solved. You take CFAR, you take ImageNet, we have progressed way, way ahead in all of these sort of academic setups. But beyond that, we have also been able to show the impact of machine learning in this standard framework on real world systems, right? So we do know that there are some autonomous cars that are being tested all around the world. They have not been fully deployed, but they're in a pretty advanced state. But then what is maybe problematic is that if you wanted to move on to embodied learning, where let's say you take a machine learning agent and you want to put this particular agent in a new environment, which this learner has never seen before. And for example, take the example of taking someone from a scenario where they learned their environment in a country such as India, and now you want to take them to a different country like France, let's say, for example. And clearly there are relations between the two countries, in terms of the physical appearances of different objects, but also we do know that things look very, very different in different countries. Like first thing is, you know, in India, you drive on the left side of the road, whereas in France, you drive on the right side. So there are, you know, things that need to be adapted even from something as simple as that. So this whole idea of sort of embodied learning, where sort of the agent interacts with other agents in a new environment, is something that is, you know, still far-fetched. As far-fetched as an idea for us to, you know, deploy in an empirical setup. Okay, so now I'll be answering the question actually that was posed about the difference between, let's say, continual and online learning. So we'll take, you know, the standard supervised learning framework, right, where we have, let's say, a particular task T1, which has a corresponding data distribution D1, from which we sample some data items, data samples, such as X. So capital X is a set of Xi's, which represent my entire training set in this case. And for each of my Xi's, there is a corresponding Yi, which denotes the label. So if you take computer vision problems such as image classification, X would represent a collection of images, and Y would represent a collection of labels that we want to assign to each of these images, which represent, you know, what are the objects that are contained in each image. Okay, now given all this data in a supervised learning setup, we have a learner that is trained on all this data, and then in a test scenario, we have the same data distribution, as I said, you know, D1, and then from this we sample new data items X to then evaluate the learner. So in this case, we don't use Y, we only use it to kind of evaluate how well the learner has performed. So now in this sort of generic framework, where are all the different types of learning frameworks, you know, with respect to each other? So we look at a few examples. I'm not covering, you know, all the different learning frameworks that do exist in the ML community today. So I'll take firstly the multitask learning, right? So in this case, what we have are several different tasks, TI, so T1 through TK, let's say, representing K different tasks. And for each of the tasks, we have a separate data distribution, right, DI. And the task of the problem of multitask learning is to learn to solve all of these tasks together. So we have one single learner, which kind of uses all the information from different tasks and then learns a model, right? Now in the test setup, what we would then have is the same data distributions, D1 through DK. And from each of these, we kind of sample the test examples. And the task will now be to actually solve each of these tasks without knowing necessarily which sample corresponds to which task. So we just want to solve all of them. So where might actually, you know, why do we want to do this kind of a learning framework is when, let's say, you have tasks that are related to each other. Like, for example, if you take task T1 being, let's say, image classification, task T2 being object detection, task T3 being, let's say, image segmentation, right? Clearly, if you know what object is contained in the image, it is much easier for you to detect it. And once you know where the object has been detected, it's much easier for us to actually go and segment it, right? So all these tasks are very related to each other. So that's where the learner, you know, would like to exploit the relationships between different tasks or among all these tasks. Okay, so moving on from that to the idea of transfer learning. So here we have two tasks, the source task TS and the target task TT, right? So the source task, we have the same idea of data distribution, samples, and then we learn a model from this, on this training data. And then we also have data from the target domain, DT, from which we want to learn a new learner, but then we also want to exploit the knowledge that has been learned already from the source domain. Okay, so this could be a case where, let's say, you have very few data samples for the target task TT. So you want to exploit a related, perhaps, task, which is source, which has a lot more data samples, and you want to use all the knowledge that you have learned in this model, then transfer that together with a few set of samples, right, that you have for your target class, target task, and sort of strengthen the learner for this target domain. Now, in this case, now we don't have to do anything with the source data in the test setup. We only get data that corresponds to the target task, and then we want to evaluate it, right? So then a related problem of domain adaptation to that of transfer learning is where you have both, again, the source and the target domains, but in this case it's one and the same task. So it could be, let's say, as an example, you want to do image classification in the case of sort of natural images, outdoor images. That might be your let's say source domain, and then you have your target domain, which is, let's say, images from the medical domain, right? So here the task is still the same. You do want to classify, let's say, certain parts of the image, but the domains have completely changed, right? From natural images in your source domain to images from the medical domain in the case of your target domain, right? So you want to exploit both of these jointly to then strengthen your learner. And in the case of test, you will get samples from the target domain, okay? So that's the idea of domain adaptation, where you want to move on from learning in one particular domain to that of a different one, right? Going back to the example that I mentioned earlier, let's say you want to train an autonomous driving system in one country, let's say India, for example, as a source domain, and you want to transfer this to a target domain, which could be a different country, like let's say France, for example. Okay. Now then, a few years ago, there was this whole idea of meta learning, which is again related to all these learning frameworks, where you have one single, let's say, global data distribution DT, right? And from this data distribution, we would sample or subsample smaller distributions D1 through DK, right? So think of this whole problem of, let's say, classifying images across 100 classes. And we might want to divide this into, let's say, smaller problems consisting of 10 classes each. So let's say domain 1 now represents the first 10 classes, domain 2, the next 10, and so on, okay? So the task is still to do image classification, but with respect to that particular domain, okay? Now using all of these, we would then construct what is called as a meta learner, okay? And once we have this meta learner, we would like to use this to then test in this meta learning setup, right? Where you would again choose a new distribution that is sampled from the original data distribution, right? In this case, let's say DN, and you sample a few examples from it, and then you want to then evaluate your learner on this particular setup, okay? Now, that is sort of briefly, what happens in meta learning, where you have meta train and a meta test setup, where in the meta test setup, you also have a phase where you actually do some training on this, let's say, target domain. And then you would get samples from the same domain, which you would then evaluate, right? So as you can see here, there is also a blue phase where you do the training in the meta test setup, right? So this idea is to make the learner and learn sort of the learner itself in terms of its hyperparameters and other things. So now coming to the online learning setup, where you have, let's say, in the simplest case, you have one single task, and what would happen is you would get samples which are extracted or sampled from the training set at different points in time. So you have a single data distribution D1 from which you get samples X1 at one point in time, X2 at a different point in time, along with their corresponding labels, Y1 and Y2. And you want to use all of them and then continue to learn the model, right? So this is a case where the model is learned in sort of an online fashion, because you get samples one after the other, okay? And what would happen then in the test phase is that at any point in time, you could be given samples from the test set for you to evaluate the existing version of your model, right? So presumably, right, the model will be much more robust as you see many more samples, whereas at the beginning, the model will not be as robust because it has not seen that many training samples to have a better model of your data distribution, right? So this is sort of the online framework where you don't get all the samples at once. You get, let's say, one sample at a time, or let's say a few batches of samples at different points in time, okay? So then we have now the continual learning setup, where in a general case, what you would have is, again, data sort of coming in this online fashion, but you would not necessarily have data corresponding to a single task, right? So here we see you get some samples from task T1, and then at a different point in time, you get samples from task T2, and so on. You get then samples from the task TK, okay? Now here, then the difference would be is that, let's say you have now learned the model through tasks T1 to TI, okay? Which means that you can evaluate on all of these tasks. So data coming from all of the tasks that you've seen so far, so from 1 through I, can be evaluated at that particular point in time, okay? And as you now finally see all of your tasks, you'll be able to evaluate data from all the tasks at one point. At the final stage, when you have learned all the tasks, learned to solve all the tasks. So you can see that, to answer the question on continual and online learning and the differences, so they are both related, but I would say that continual learning is a more general case of online learning, where you do get samples sort of, you can say, sequentially, but in a general case, the tasks can change. We'll see what we mean by changing tasks. You can also have the classes that change, and the difference here with online learning also is in the test phase, where you get data from only one single distribution, right, to then evaluate the model. Whereas in the case of continual learning, you would get data from different distributions which correspond to different tasks. So there is another question: is domain adaptation a subcategory of transfer learning? Yes, domain adaptation is indeed, you can say it is like a special case of transfer learning. So again, there would be an overlap among many of these frameworks that I'm speaking of right now, but they won't be exactly the same because one is more generic than the other. And for example, domain adaptation would be a special case of transfer learning, and then there could be also variations in terms of what are the labels that are available. So you could have cases of transfer learning where you only have labels for samples from the source training set. You have samples from the target training set, but you don't necessarily have labels, or maybe you only have a subset of the labels. So that would be another type of transfer learning, or what is called as unsupervised or low supervision transfer learning. Right? And similarly for domain adaptation, you also have unsupervised domain adaptation, etc. So here I would say there's a big overlap between transfer learning and domain adaptation. Okay, so this is just to give you a very high level idea of some of the popular learning frameworks. Okay, and in this particular lecture, what we're going to be focusing on is only this aspect of continual learning. So we're going to define it a bit more systematically, so we see what exactly we mean by continual learning and which particular setup that we're going to handle in this lecture, right? Because we could see many variations even within continual learning. Okay, so complete my slides there. Okay, so now this incremental or continual learning setup. So what do we have here? So we have different tasks showing up at different points in time, and for each of these tasks we have a corresponding data distribution, right? For task T1, you have data 1. So what could be these tasks? So these tasks, for example, could be that of, let's say, image classification. T1 could be that of classifying, let's say, different types of animals. Task T2 could be another image classification task, but on a completely different set of classes, which have nothing to do with, with each other in terms of flowers, let's say. And T3 would be different types of, let's say, vehicles. T4 could be sports, and so on. Okay, so this is something that is typically called as task incremental learning. Okay, where we have tasks represented by different problems coming in at different points in time. You can also have what is called as a class incremental learning, which is actually an example that I show you here, where you have the one single problem of classification, but then here the classes on which your problem is acting on are different. right? Going from animals to flowers to vehicles, etc. You can also have sort of, let's say, let's say an intersection between domain adaptation and incremental learning, and have something called as a domain incremental learning. So let's say you want to have classification starting from, let's say, outdoor scenes to indoor scenes. So the domains have changed from outdoor to indoor, and then we can have even more dramatic domain change going from, let's say, an indoor setup, outdoor setup to, let's say, the medical domain, where you have nothing to do between the two domains. Okay, so these are all possible versions of incremental learning. Okay, and we're going to be mainly talking about sort of the task or the class incremental learning in this lecture. So this problem, is not something that we've invented in the recent past. It's a classical problem in machine learning which has existed for many decades now already, and it also has relations to other types of learning which I haven't mentioned so far. For example, zero-shot learning is one extreme case. You can sort of think of it as incremental learning or continual learning, where you have absolutely no training for the unseen classes. You train your model on a set of classes, and now you move to a completely different set of classes for which you haven't trained your model on, right? So this is a case where you have zero training examples for a class. Okay, another method that was presented in this framework is that of continually updating the training set, right? So we said, okay, you start with some training data, and then you continuously accumulate new training data. So one potential solution could be actually to, okay, I'll just decide to keep all of my data and then just simply retrain my model, which is a feasible solution. But then it imposes certain restrictions in terms of what is the capacity of your model, what is how do you say, what is the capacity of the training data that you can hold in your let's say computers or clusters, etc., to train your model, etc. So that imposes certain restrictions. Another solution that comes up frequently is that of using, let's say, a fixed data representation. So these days, in the last, let's say, 10-15 years at least, what we are going for is sort of models which learn not only the classifier or the model that will help you solve the problem, but also the representation that transforms your data into sort of feature vectors, right? So these two steps of the learning framework have sort of been combined to bring out all these end-to-end learning frameworks through, for example, deep learning or neural network models, where we combine these two tasks and then sort of solve it end-to-end, starting from, let's say, images in the case of visual or computer vision problems, to sort of labels that we're interested in, such as image labels or segmentation labels, etc. Right? So this kind of complicates, the way that we can deal with incremental learning. So one potential solution which has been used before, let's say, the era of deep learning, is to have a fixed data representation through, your favorite feature extractor, which is not learned per se from data, which is kind of like a direct algorithm which doesn't have any learning involved in it. So, right, for example, SIFT is one computer vision example that I'm thinking of right now. And using this, we can simplify the learning problem, because we now only have one of the two tasks to solve of learning the classification problem. Okay, so there are sort of alternatives that are available, but then they come with their own pros and cons. So there's another question. I'm wondering, what's the exact meaning of domain? Different domain mean different data sets? Yes, different domains do indeed mean different data sets. So domain is something where, let's say, you have for each data set, there is a distribution from which the data was, created. We don't know what exactly this distribution is. Like if I ask you, what is the distribution of ImageNet? How would you describe it? We can't put it into a single equation. It's sort of a distribution that is sort of unknown. But all the images are from that particular distribution of, let's say, natural images, right? But now a different domain would be one where I completely change the domain from, let's say, these natural images to acquired images, such as MRIs, for example, which are sort of man-made images when we measure different aspects of the human body. So that would be kind of changing the domain completely, which would imply a different data set. So I would say it's sort of a different domain would imply different data sets, but different data sets don't necessarily imply different domains, right? For example, you take, let's say, CFAR versus, let's say, ImageNet. So there is, some domain gap between them, but it is not as dramatic as, let's say, the domain gap between medical images and outdoor images, right? So yes, different domains would mean different data sets, indeed. Okay, so let's see, what can be the solutions for tackling this problem of incremental learning. So let's describe the original model that we have, right? So here I'm using a deep learning model to kind of describe, what is happening to my, how I'm solving, my task. So you have a test image shown on the left here. It is passed through a series of deep learning neural network layers. And then finally, in the last layer, we would be able to kind of solve the task that we're interested in. So this is, let's say, the original model that we have. So I'm calling it old tasks because this is the initial set of tasks the model is capable of solving, okay? And you have M of these tasks. So now what we have is this original model. And what we would like to do is to kind of extend this model to new set of classes. So let's say you have one new task, which means you have the ground truth, so the samples and their corresponding labels for this particular task. And what we might want to do is, okay, we take all of the data that comes from the old tasks 1 through M, and then also the new task. Let's say it's only one of them. So you have M plus 1 tasks for which you have data, the old data, and then the new data, okay? The joint training, or what I call as sort of the golden baseline method, would now be actually to take all of this data, put it together, and then just simply retrain your entire network, right? So it's a standard thing to do. Fine, we can change all the parameters or we can allow all the parameters of the model to change given this new data in combination with the old data, right? So what this will do, this step of retraining the full model with both the new and the old data, what it actually affects is your feature extracting part and the classification part. All the parameters have been changed, right? So initially this is the network that we have with the feature extractor part and then a classifier part. Now we add the neurons that correspond to the new classes in the classification layer, and then we just simply retrain the entire network, right? Both the blue boxes that you see here. Now this is great, but as you can imagine, it can be computationally very expensive, right? Because you have a lot more data to handle, and you just keep increasing the amount of data that you need to handle. And also in some ways, you're kind of redoing the entire training framework, which has already been learned or executed for the previous tasks. There could be some smart ways of doing it, which, let's say, kind of not learning all the parameters, but in sort of the brute force solution that that we are looking at now, we just do it for all of the network, all the parameters, and using all the data. Okay. The other important restriction with this framework is that you need access to the old data, right? And this kind of puts limitations on in terms of what is the storage capacity, right, that you can handle. So clearly, data can grow, and you can store a lot more data now, but at some point, this would break. And more importantly, you could have some privacy issues, because maybe the data that the initial model was trained on cannot really be shared beyond the initial developers of the model. But it might be okay for you to, let's say, share the model itself, but not the original data that the model was trained on, right? And then you have sort of scalability issues, where you are not really adapting the initial network which corresponds to feature extraction, and what you're doing is just simply extending the classification layer, right? So each model has its own capacity in terms of how many classes, let's say, it can handle, and this can grow, but at some point this would create an issue of scalability, right? So to sum up, why do we not want to do a brute force kind of solution is, we don't necessarily have access to all of the data, or we can necessarily not store all of the data, or let's say maybe we have access only to the previously learned model, as in somebody has trained the model on some data and just shared you the architecture and the parameters of the network, right? So, and this is a common thing that for those of you doing computer vision, it's one of the most popular things to do, which is to kind of use a pre-existing trained network and kind of fine-tune it according to your own needs by, let's say, removing the last layer, putting new last layers, etc. Okay, so this is something that we all do, and it has been very successful. So it could be the case that maybe the people who created the initial model cannot share with us all of the data. So we would be limited by this brute force solution. Okay, so let's start looking at sort of maybe a couple of naive solutions to this framework. So just to recap, this is the original model of this of this network. Okay, so now what I would do is maybe I would decide not to change all of my initial layers, okay, that you see here in these unfilled boxes of your network. And then what we will do is only train the parameters or learn the parameters of the new part that has been added to the network. So for example, let's say you have a few layers in that deal with the classification of the model, and you just add new components only to these layers. And we initialize these parts of these layers, and then we train using only the new data, right? And the rest of the model is kind of frozen in some ways. Okay, so we don't touch that at all. Okay, so here all the sort of half shaded region here is something that is not being affected by the new training setup and the new data, and only the part that has been added is being trained, right? So clearly this is doable, but it can lead to suboptimal results because the features that were extracted for the new task are not really adapted for this particular task, right? So in this case, let's say you have a classification task for, let's say, 10 classes, and now you extend it by adding, let's say, another 5. Excuse me. So for these new 5 classes, the features are sort of irrelevant or not really appropriate. Okay, so now we want to move on from this poor naive solution to perhaps a more useful naive solution, where we'll say that, okay, we will modify not only the part of the part of the network that was added for these new tasks, but also we will fine-tune all of the previous layers. Okay, so this could be done in like sort of several ways. The extreme case would be the one in naive solution, where we don't fine-tune any of the layers, and the other extreme would be to actually fine-tune all of the layers of your network. Okay, except the part corresponding to the classification for the old classes. Okay, the boxes that you see here, which are unfilled. Okay, so now the part of classification is the only one that remains untouched or frozen, and the rest of the network is either fine-tuned or kind of learned from scratch with the random initialization for these new classes. So this is great, but it leads to this phenomenon which is known as catastrophic forgetting. Okay, so to understand this, let's see an example, and maybe here is a point actually where I'll try to ask a few questions, and then we'll see if we get any responses. Okay, so before that, so let's set up the problem that we're interested in. So the popular task of, let's say, detecting objects in computer vision, right? So given an image, what we would like to do is identify where the different objects are in the image. So here is, let's say, the model was initially trained for the person, let's say building, and a few other classes. So here you're detecting, let's say, a person shown with this green bounding box and the label that says person on it. Okay, and let's say this model was initially trained on 3 classes, for example, person, building, and let's say trees. Okay, and we're only showing one result, from this test image. Okay, so now what I would want to do is also not only recognize or detect where the person is, but also I would like to detect horse. Sorry, we'll take this question. It's about the previous slide. So what is the difference between solution 1 and 2? So I'll just quickly go back. So this is solution 2, right, where I'm also modifying the feature extractor part. And so all this fully filled region that you see here, feature extraction, and this part at the bottom for classification, the parameters of these layers will be modified, right, by using a new data. This is solution 2. And solution 1 is the one where we don't touch the feature extraction part at all. We just simply only modifying this. So this will become sort of half shaded. If I just go back a couple of slides. So this is solution 1, where we are not training, or fine tuning any of the layers that correspond to feature extraction. Okay, so that's the difference. And each of them, has its own pros and cons. So this will clearly be way faster to train, but it will not be optimal. Whereas this one will be leading to a phenomenon called catastrophic forgetting that we're going to define now. Okay, right. So that's the difference between these two naive solutions. So now this is my tasks. So in addition to recognizing my initial 3 classes, I also want to now be able to detect my 4th class horse, right? So ideally, now get this bounding box around the horse, which represents where horses are in images. And ideally, you also want to still be able to detect where the person is, right? Which is, let's say, your class number 3, and 4 is what horse is. So for the purposes of our discussion, let's call the top network, which was initially trained on 3 classes for detecting 3 object classes, as A. And then let's call network B as the one where you add new classes and you'd like to detect the entire set of classes from the image. Okay. So let's take this problem to the case of, I think this was Pascal VOC, where you have, let's say, 20 object classes. So I will call the first 10, so 1 to 10 as my old classes, because that's what the model was initially trained on. And then I'll call my classes 11 to 20 as my new classes. So these are like, common animals such as cow, sheep, and also people, objects such as table, chair, etc. So these are the 20 set of classes that are in this particular data set. So here I've just simply computed, you get the overall accuracy on all of the classes, obviously, but we can also compute the accuracy of detecting objects on the first 10 classes, which is this 68.4, and then the next 10 classes 11 to 20, which is 71.3, right? But in this case, all of them were trained together. There was no sort of continual or incremental learning. So now we'll look at the incremental learning setup that we had earlier. So this initial A1 to 20 is actually like my golden baseline, right? As I was calling it earlier. So this is the best, that we can do with this data set for this particular problem on this test set. Okay. So let's take the case of this initial model, which let's say was trained only on the first 10 classes, right? Which is my initial set of classes or my old set of classes. So this will give us a performance of 65.8, which is lower than what you would get from the initial or the baseline or the golden baseline. We can't compute this value for new classes because the model has not been trained on any of the new classes. But my first question, a simple one, is actually, why do we see a drop in performance on the old classes? Feel free to, I don't know if people are allowed to answer questions on the chat. I suppose they can. Let's see. I'll just wait for a second or two to see if anyone can say why we see this drop in performance when we go from training on all the classes to training on only 10 classes. Any answers? Okay, I see. There will be a delay, no problem. And yes, the answer is more data in all classes. Indeed, in this case, the more the data, the better the model would be. In some ways, these 20 classes, they don't include the background class as such. Yes, 10 classes sorry, I'm just reading another answer, a few answers. Yes, indeed, you have a lot more data to train when you are training on all the 20 classes. And also you build a better model of, let's say, background. You don't get like false positives because you have seen more classes and you know which is your background and which is not. Okay. Right, so now let's define then the other model where you have your initial model A, which is trained on 10 classes. Now you want to extend this to the model B by adding 10 more classes. So you want to train with this new set of classes. So here I would now actually take some more answers. So what do you think will be the performance of this network B on all these 20 classes? So what will be the performance on the old classes and the new classes? Any guesses, answers, roughly? So B is a network where it was trained initially on 10 classes, but now I use data from the new classes and retrain this model by, like I said, the naive solution 2, where I'm fine-tuning, let's say, all the previous layers, and then training the classification layer for the new classes. So I'm trying to see if there are any guesses on new classes will be better, old classes might be worse, indeed, but maybe can someone give me a ballpark figure for where would the old classes be? Old, very bad, yes. So I'm reading the answers. New would be good, but maybe not as good as the baseline solution. Old may fall. Okay, right. So that I think several of you have got the idea. Indeed, the performance on the old classes would dramatically decrease. And in fact, here, just for illustration purposes, I've done the most extreme case of, let's say, fine-tuning all the layers. So indeed, it is dramatically low, just about 13% compared to, let's say, the 68 in the best case that you had. Okay, whereas the new classes is indeed significantly better compared to the old, because you just retrain the model on these new classes. And as expected, it is still lower than 71 when you are able to train on all of the classes together, because it gives you a lot more data in one single step. And obviously the average of these computed over all of the 20 classes would also be significantly lower because of this catastrophic forgetting of your old classes, right? So this is like, it is not a great surprise, because when we are doing this retraining or fine-tuning, there was no guidance, for us to kind of capture or retain the information that was learned from the old classes. So there's a question: training with new set of classes will forget the info of the old classes. Indeed, so that's exactly what is happening. We are forgetting pretty much everything we learned, or most of the things that we learned about my old classes. Also because we did not allow this new model to kind of retain any of the information. So clearly now we need to find ways in which we can retain this information for these old classes. Okay, so this kind of illustrates, how bad the performance can get. Now we'll see sort of, the remedies or potential remedies for solving this. Okay, so let's formalize a little bit, the incremental learning by defining, let's say, some rules in our setup. So, like I said, we have. So let me take a question in the meantime, just before I advance. Sorry, what is the method here to add B based on solution 1 or solution 2? So this is using solution 2. Okay, we are fine-tuning the network, so which means that the model is really heavily adapted to solution 2, which is also the right thing to do, but maybe there are ways of handling this fine-tuning. So what we have, B, is the result that I showed you earlier is with solution 2. There's a second question: what kind of guidance for retraining the old classes? So this is what we will see in the next few slides, of what is the guidance that we can give to retain the old classes. Okay. So before that, we'll set out a few rules for incremental learning, where you have multiple tasks, okay, coming in sequentially, and you want to learn one task after another. So this is one, but you can also think of a variant where maybe you don't have just one task coming in at one point, but you have, let's say, multiple tasks coming in at different points in time. So that is also sort of the incremental learning framework that we are going to consider. The other constraint that we want to put in this framework is you don't want to store data from previous tasks, right? So the strictest thing that you want to apply is not store any data from the previous tasks, right? And the reason for this is also that you don't want to have a memory footprint that is growing over time, a memory footprint which not just deals with the data, but also even the model capacity as such, right? You just don't want to keep growing the model infinitely large, because you have certain restrictions on what you can do with this incremental learning framework. Okay, then we also have another constraint in that you don't want to, let's say, forget any of the old tasks for which the model was trained on. Okay, so these are the 4, let's say, ideal rules that we would like to apply. But we're going to relax these rules a little bit because achieving this is practically, impossible. So this now we'll make sort of certain adjustments to these rules by saying that, okay, instead of storing, let's say, none of the samples, what we will say is, okay, we will not store many of the data samples from the previous tasks. Okay, we might store some, but not all. The other thing that we would want to do is maybe the memory footprint that we have, we don't want it to grow significantly over time. We'll allow it to grow a little bit, but not significantly. Okay, and finally, the 4th rule, we will say that, okay, we will allow the model to forget some of the old tasks, maybe not just all of the old tasks. So this is in some ways what happens also with human learning, in that clearly we do forget some things that we have learned in the past, but we don't forget everything that we have learned in the past, in most cases. Right, so that's the sort of relaxed set of rules that we would like to apply for this incremental learning framework. Okay, so this brings me to what exactly are we going to see in this particular lecture today. We will see some different flavors of approaches for handling this problem of forgetting the old tasks. These will be sort of categorized into three types of learning frameworks, which are regularization based, which are rehearsal or replay based, and then also some which are sort of architecture based. Okay, and then if there is time, maybe we will see a different problem, also in addition to classification. So most of the things that I'm going to be covering in this lecture will deal with the problem of image classification, the methods that I just described briefly. But if there is time, maybe I'll talk a little bit about solving other problems than classification. And then we will end with some sort of takeaways from today's lecture. Okay, so we're about 50-ish minutes into our lecture. So I'll continue a little bit more, and maybe roughly around the 1 hour mark, we will take a short break. Okay. Right. So the first one first, let's say, class of approaches we'll be handling is that of regularization based. Okay. And there are several methods, that have been proposed, and here are just a few examples from this. So in sort of a couple of phrases, what exactly are these regularization based models? What they try to do is, when you're training a new task, you kind of add a regularization term to the loss. So this is the most natural thing, coming from, it's an optimization or a machine learning background. You will say, okay, hey, I have my loss function. I now train my new network, but when I'm training my new network, in addition to having my, let's say, cross entropy loss on the new classes, I will also have a term which kind of regularizes and pays a penalty for, let's say, changing the network too much with respect to the old tasks. Okay. So that's sort of a regular thing to do. You do it for SVMs, you do it for several other machine learning models as well, and also in optimization when you're trying to kind of regularize a particular solution and not to have it kind of go completely crazy in terms of, I guess some people also call it the Occam's razor, to kind of have a simpler solution. Maybe you want to add another penalty term. So in a sense, for this particular case of incremental learning, what we will do is we will sort of add a term for regularization, which will penalize this catastrophic forgetting. Right? We'll see what possibilities we can have for doing this penalty, and I'll talk about two of them. The first one could be sort of a data-focused approach, and the second one could be more like a model or a prior-focused method. Okay, so these are the two, let's say, flavors of regularization that we will be discussing today. Okay, so let's see what is my data-focused regularization. So one popular example here is actually that of this paper from a few years ago now already, which is called as learning without forgetting. Okay, and here they use an idea from the machine learning community, which is that of knowledge distillation, right? So this was an idea, a paper from the University of Toronto, if I remember correctly, where the idea was to kind of distill the information that you have learned for one particular model, from that to a smaller model, which has a much lower capacity in terms of storage or the memory footprint, that is the number of parameters of the model. But you would not like to have a big loss in performance when you go from a much more complex and larger model to the simpler and smaller model, right? So this is the idea of sort of knowledge distillation, that you want to distill the knowledge from a more complex model to a less complex model in terms of, you know, size, etc. And this paper actually used this idea in the context of incremental learning by saying that, okay, what I would like to do is kind of distill the information that I have from my old model, okay, to that of my new model, by kind of preserving the responses that I get when you give, let's say, a new sample to your old model versus giving the same sample to your new model. Okay, so so what actually happens here is, I think, right, so we have two losses, right? The first loss acts on the previous model's output for the old tasks, right? So you take a new task or a new sample as input, you extract its features, you pass it through all the layers, then you get some results even for the, you know, the old part of the model, which corresponds to the layers for classifying, you know, the old classes for the image classification problem. And then you get responses from the new part of the layer, okay? And from the new part of the layer, right, we have our annotations to be able to kind of learn with the cross entropy loss, the weights of this particular layer. But what I'm going to do here is also going to compute a loss with respect to the output that I'm getting for these this part of the layer corresponding to the old classes, because the model has changed, the weights of the feature extracting part have changed. These responses will be different to what you were getting previously. So you store a copy of the previous model and get those responses and compare them with respect to these, okay? So, and how do we, sorry, I forgot to mention, how do we define this particular loss? You know, the simplest thing that you can do is just simply do a L2 loss between the responses that you get now for the model, whereas the responses that you get from the previous version of the model, okay? So, which means at every stage, you would have, how do you say, two copies of the model that you will store, okay? So this is some form of guidance, you know, to answer one of the questions that we kind of give our model. So what is great about this model is that, you know, it's a very, very simple method, right? And it has also shown actually good results on related tasks, in that if the tasks could be, let's say, recognizing cats and dogs, to moving to recognizing, let's say, horses and cows and other types of animals, the results are actually pretty good, okay? And there is a problem though, in that there will be poor results for unrelated tasks, right? That is one of the problems with this model. And there is a question on, you know, okay, how much can I actually store? In this particular case, we do need to store the old model so that we can compute the responses of the old model, which was untouched by the change, you know, that we are doing for this network. So basically, in the example that I showed you earlier on, where you had the version A of the model, and then you have version B, which is the updated version of the initial A, you would just store both A and B. So you double the number of parameters that you need to store. Right. Yes. So I didn't mention, sorry, I'm kind of skimming through these methods. So maybe I'll just go through quickly on what exactly we do here. So you have, sorry, I should have mentioned these colors that we had earlier, right? So a box that is fully colored is something, where we are changing the parameters, where we are fine tuning it. So in the case of this learning without forgetting, we are actually retraining the entire network. So previously for my naive solution, I had this box which was being changed, this part of the layer being changed, whereas this part corresponding to classification of the old tasks was not changed, right? If you remember, it was shaded, half shaded, this classification box. Whereas now in this case, given that you have some loss that you can compute, which is the difference between the responses of this network, the modified network versus the unmodified network that you had, right? You would get the difference between two of them. Okay, so you are also changing the parameters of this part of the layer compared to the naive solution. So the reason you didn't change it in naive solution 2 is because you had no data and no way of kind of computing some form of ground truth to modify this. But here you have a new loss, which is looking at the previous and the current responses. Right, so that's the answer to question from Andrea Panizza. So then there is another question, where is the regularization in this method? So the regularization in this method is on the part corresponding to the old classes, which is the previous model's output. Okay, so that's where the regularization is acting. So kind of speaking in a hand wavy kind of approach, what we're trying to do is, okay, you're allowing the model to change, right? You have this cross entropy loss, which will allow you to change the parameters of your model. But then you are also kind of restricting these changes by saying, hey, the responses that I'm giving for the old part of my network should not be very, very different to what they were in the previous instance of the model. Okay. So in some sense, you don't want the model to go completely far away from where it was initially. Okay. So we'll see maybe a few visual representations actually of what exactly is happening. And actually that will be in the case of a different type of regularization, but regularization nevertheless. Okay, so then next question is, let's say we want to relearn twice. Yes. Would we keep the original base model for the second relearning task or the one resulting? No. So you always have only two. So which means you first keep the initial model, then you do the updating. So you have now your version of B, the updated model, and then you take the updated model B and you replace this with replace this for A. So basically A is now my B, the current new model becomes my old model, and then you add. Okay, so at every stage you only keep two copies of the model, the initial one and then the updated one. And once the updated one has been processed, you kind of replace the initial one by the updated one. Yes, so this answers two questions about, okay, we don't store n models for n tasks, we just store only two at every stage. And at the end, you only use the final updated model. You don't use any of the previous models to do your classification. Okay. So how does the error term look? I don't know if I have equations for all of them, but here, let's say, it's the L2 difference. So if you have your weights as Wi prime as your initial previous weights, and then Wi double prime for your new weights. So it's just a difference of them and then squared and summed up over all the weights. Okay, that's the regularization loss. And here in this case is L2, but you can think of other types of losses like an L1 loss if you want to introduce some sparsity, etc. as well. So I'm just checking if I've answered all the questions. How does the error term? Okay, and yes, and the last question on this topic was, here we will need to test. We will need test data from the old tasks as well. Yes, indeed. So there is no guarantee that it will be from only the new tasks or only the old tasks. And when you're given a sample, you don't know whether it belongs to the old classes or the new set of classes, right? You're just given a sample And it's now up to you to decide which of the class is old or new and which one from these it belongs to. Okay, so this is to be done automatically also, right? So if, when I didn't talk about all the possible naive solutions, we can have other naive solutions where you do like a two-phase thing where you first decide, okay, I want to keep like one model for each of my tasks, and I'll just simply decide which of the task models I'm going to use. Okay, so you could also have other naive solutions, but clearly we don't want to use any prior information. You don't know which task, excuse me, the data is coming from when you're testing the model. Okay. Right, so that's what we said about regularization, and then we'll see the other one, which is a model-focused approach, where you want to penalize sort of not the, let's say, the final outputs that you get from your classification layer. So let's say, here you have a logit, the logits that you compute at the last layer of your network, and you're kind of looking at the difference between the new logits and the old logits. Okay. And in this case, what we're going to do is now not just look at, stuff from coming from the data and the responses to data. Here, what we're going to actually look at is directly the parameters itself. So you have theta representing the parameters of your model, and you have k of these parameters, and n represents, let's say, the current nth version of your incremental learning step. And n-1 is the previous version, which was trained on, let's say, n-1 task, and now you're trying to add a new task n. Okay. And what we would want to do is kind of, okay, make sure that you pay a penalty if the parameters have changed significantly between the previous version of the model, n-1, and the current version of the model, n. Okay. And you want to do it for all the parameters, but clearly you don't want to do it equally, let's say, for all the parameters. For instance, the initial layers, the parameters maybe are less critical for you to make changes, and also maybe they won't change as much. And here you might want to have, let's say, a lower penalty for some of the layers that come further down in the network, because they are kind of specific to the model, right? If you have seen some visualizations, I think, of the filters that are learned in different parts of, or different layers of a deep learning model, you see that the initial layers are very, very basic features, which means that, they are kind of generic and you don't want them to change so much. Maybe you have higher weights for making changes on the initial layers. And as you go from one layer to another, sort of more deep into the model, you realize that actually the features get more and more specific. And perhaps these are the ones which should have these low weights lambda, so that they can actually change and become more specific to some of the new classes. Okay, so that's the idea that we want to use. Oh, sorry, there was a question. How do you know if a model will perform good on new unseen data, even for the same classes? So yes, so there is no guarantee. The hope is that you have sufficient training data for you to update the model when you're doing this learning framework. Okay. So there will, sorry, to complete answering the previous question is that yes, there is no guarantee initially, but the hope is that you have sufficient strong training data to learn the new classes, because you're also getting samples from the new classes. It's not the unsupervised case where you don't have any samples from the previous ones. And next question from Roman again is, if the parameter positions do not match fully connected layer, then you will be penalized wrongly. I don't know if I understand all of them. Actually, this parameter thing is applied only for the parameters that already exist, right? So you would, in the case of this example here that I've shown, you'd only apply to, let's say, all the weights in the feature extraction part and all the weights in the classification part corresponding to the old tasks, which means these, they do not change, right? These are parameters or nodes that exist throughout the network. The new ones that you get, clearly on these, you cannot put this penalty of changing the parameters, because you did not have these previously existing. So you just have to keep track on what are the new nodes that you're adding to your model, and then make a difference with respect to only the ones that are existing. So you won't have a mismatch between the two models. Okay, so now Simon asked an important question. How do you actually learn these lambdas? So this is the next part that I'm going to talk about, okay? But before that, just to recap, so the first part of this loss is the loss on new tasks, okay? Right, and then the second part is what our regularization is. So I'll just finish the slide, and maybe we will take a short break because we've already more than an hour through the lecture. And yes, thank you for the reminder. Right, so then we have these different, the lambdas that we need to assign or learn for different parameters of the model. And there are different variants that are possible for learning this importance. And we're going to see all of that just after a short break. So what we're going to do now is break for a few minutes. And is 5 minutes okay?
Yes, good.
Yes.
Yeah, back after 5 minutes.
Yes, at quarter past the hour. So I guess it's 9 p.m. perhaps for you. And so we'll be back at, let's say, 9:17, let's say.
Okay, 9:17.
Yeah, great.
Thank you.
I'll see you all in just a few minutes then.
Yes, see you later.
Great, so welcome back. So we'll continue with the model-focused regularization, right? So we said that this is the form of the generic form of the loss function. Let's say the first part is the loss on the new tasks, which can be, let's say, your standard cross entropy loss. And in the second part, we have this regularization, which is acting on the weights of the network. So in the extreme case, all the weights of the network which existed previously. So here I'm showing an example to answer one of the questions, an L2 loss for this regularization term. So it's just an example. There are different variants that are possible for this regularization. It can be an L1 or a different type of loss function. Also, there are also different possibilities for computing this importance. So this leads to the other question of how do you actually learn these lambdas? And these are sort of computed in different ways. So there is this particular paper from about 4 years ago or so, where there is a individual penalty for each of the previous tasks. So in this case, they were actually storing all of the previous models, and they were computing the change with respect to all of them, right? So which means you have a lot more lambdas and a lot more parameters of the model that are stored, okay? And the lambda in this case was computed as a Fisher information matrix on the data, sorry, on the parameters in this case, okay? And I'm not going to go through the details of this, but just to give an example, this is one way of computing. So I'll talk more about it intuitively. What are we trying to do here? So imagine you have task 1, and there are only, let's say, 2 parameters in your model, theta1 and theta2, and let's say this is the space of your loss function, okay, where the blue regions, the darker the blue, the lower the loss is in this 2-dimensional parametric space. And what we start with is some initialization somewhere, and then we do our gradient descent in this parameter space, and then ideally reach this yellow dot, which corresponds to the local minima for both of these parameters, theta1 and theta2, for this particular task, right? So now if we consider, let's say, task 2, clearly the space of these parameters would change, and where the ideal location is for my solution will also change, right? So in this illustration, here is where the initial solution was coming from task 1. And now you do just learn, let's say, on task 2 without any regularization, you would kind of end up in this local optima for task 2, right? And if you were to transport this point into the original parametric space for task 1, so clearly it is not the best solution, right? So what we would like to do instead here is to move in this particular direction. So you want to guide how this initial point moves for task 2 by using information from task 1, right? So by moving in this, let's say, yellow horizontal direction, you would get a good solution for task 2 as well as task 1, because you're remaining in this local optimum space for task 1. Okay, so that's the sort of idea behind using these regularization terms, and that's what we're trying to do by kind of using terms such as these. Okay, and in this case, they chose to use the Fisher information matrix defined by these parameters. So in the case of elastic weight consolidation, what we would end up with is, so the gray region here is the optimal region for task A, and then this beige or creamish region here is the ideal for task 2. And what we would like to do is sort of remain in the space that is common to these two tasks, A and B, okay, and not just go away from following this blue arrow. If you were to use no penalty, you would swap from ideal solution for task A to directly the ideal solution for task B, which is nowhere near as good for task A. And in the case of elastic weight consolidation, you're doing this Fisher information matrix, so you kind of stay along, let's say, the axes of the elliptical region here, assuming that it is an ellipse for the illustration purpose here. and you would end up in this region, which is also good for task A and B. And if you had an L2 penalty like the one that I showed you earlier on, you would kind of go to something that is not great for neither task A nor B. Okay. Sorry, there's a question. Okay, so what kind of parameters can be seen as important? All the weights of the network. So you would consider all of them, but you would compute the value of the Fisher information matrix. So think of it as like, some ways you can also look at it as the entropy, right? So you would want to give maybe, let's say, high weight for ones that have a higher entropy versus whereas the ones which have a low entropy, maybe you want to give a low weight. So that could be one way of defining which are more important. Another, a simple but more tedious way would be like you have a network, and let's say you change one of the parameters of your network, then you see how it actually affects the accuracy. So in some ways, you want to measure the sensitivity of the model to each of the parameters. So this is clearly a very expensive operation if you want to do it for all of the weights in your model, but it is a potentially feasible solution where you do this, and if the result has changed significantly, it means that it is a very important parameter which should not be modified so much. So you give it a higher weight for modification. Okay. Right. So there's another question, why it needs a penalty for each previous task. So we need this penalty for each of the previous tasks because we want to avoid this phenomenon of catastrophic forgetting as much as possible. So we will not have time, unfortunately, to cover how this Fisher information matrix is computed, but I've put the reference in the slides here. These will be available after the lecture today, hopefully tomorrow, and you can see the reference from this paper of elastic weight consolidation, Kirkpatrick et al. And they talk about clearly, how you compute the Fisher information matrix, etc., etc. So it's a fairly standard thing, but let's keep it away from the discussion. I don't remember the title, but it should say elastic weight consolidation somewhere. I'm sure you'll be able to find it. But I'll put these slides up online, so you'll have all the names and the references. Okay. Okay, and I think it's a paper at PNAS. Yeah, that's how they call it, I think. Right. So what is good about this method is that it is very agnostic, completely agnostic, in fact, to the architecture, and it has shown sort of good results, but only empirically. The slight downside to this is that you're kind of doing this approach in a very local kind of phase, where you look at each and every parameter, you're looking at the difference, and you're summing over all of them, but still there is no sort of global some globalness as such to this solution, because you don't have any idea of which of the weights are from a single layer. So that could be potential improvement. I don't know if there were follow-up works to this, but perhaps this could be done in a sort of layer specific fashion. Okay, to kind of at least keep some of the group based or global information at least at each and every layer. Then clearly, yes, there is a memory footprint that is attached to this, which is that for each and every parameter, you have a weight that is associated with it, either from your Fisher information matrix or in another form. Okay. Okay, so there was a slight modification that was proposed for this approach, slight in one way, but then you could consider it as a big change, maybe in some other ways of computing the lambda. So the one change that was done is not to consider all of the previous tasks, but only one previous task. So this is like the previous framework where I was talking to you about, where you have the current model and just maybe the previous version of the model. Okay, so you always have only two. So that's one important change that this method called memory-aware synapses had proposed. And another one is in terms of how they compute the lambdas. So here they looked at directly actually the change in the gradients, right? So you had a lambda, which is a function of the gradient that you compute for updating a particular parameter versus the gradient that you had for updating the old version of the model. So the change between these two gradients is what this method from about 3 years ago had used. And I don't think I'll be able to cover this, but then they look at not just not just locations where the samples are available, but they also do some sort of interpolation by looking at this samples in between the measurements that you have. So here you see these sort of blue dots on the curve, which represent the data distribution. Okay, and for each of them you have how do you say, a label that is associated with it. And for all of these, you would kind of sample more intermediate samples in as well. In addition to these yellow dots that you have, you see all these orange samples that were extracted. And for these, you interpolate the label, and then you use all of these samples together to kind of then extrapolate and compute the difference in gradient. Sorry, I'm kind of speaking at a very high level and sort of very hand-wavy for the solution, but I think the important thing that we should take away from here is, okay, we are imposing a restriction on the thetas or the parameters and how they are changing between the incremental steps. And the other important thing is that, okay, each of these changes we can kind of weight with a parameter lambda, and how we compute this lambda can vary according to the different methods. In one case, maybe use the Fisher information matrix. In another case, maybe compute the change in gradients. And this can also be done, as shown in this graph, actually more smartly for the change in gradients by not just using where the samples were initially present, but also kind of sampling additional unlabeled data also. Okay. But again, I would refer you to the actual papers, which would give you the full details of how exactly these lambdas were computed, and some of these works also have implementation available. Okay, so then what are the advantages of this second type of model-focused regularization? It is sort of agnostic to the architecture again, right? Because you're not looking at anything specific in terms of the architecture. There is also an advantage in that here you're leveraging both the data, right, for computing the these lambdas, and also the output, because gradients are coming from the output, right? The output for which you compute the loss and for which you compute the gradient. So in some sense, it is kind of a hybrid approach between the model-focused ones, like the elastic weight consolidation, which is purely model-focused, and which uses only the data, versus this memory-aware synapses method, which uses also the output, okay? Because you're indirectly using the gradient for computing the lambdas. So it kind of makes a bridge between, the purely model-focused and maybe the purely data-focused approaches. But again, it has the same problem of being only locally valid, because you're not doing anything global. There is no information in terms of the layers of the model, etc. Okay, and there is still the restriction or requirement rather of having to store sort of your weights of this for all of these parameters of the model. Okay. So we talked about sort of two examples of model-focused approaches, this elastic weight consolidation, memory-aware synapses, very, very briefly, I should also say. But then there are several other alternatives that have come up in the last 4 or 5 years. Here are just a few examples from some of the more older references, but still equally relevant today. So this, again, you'll see it on the slides. So then maybe I'll go through the next flavor of these approaches in terms of rehearsal or replay. Okay, and there are again several approaches here. We'll take a look at a couple of them. So the general idea in this rehearsal or replay based methods is that you store, let's say, a couple of examples from the previous task. So we are kind of relaxing one of our rules, right, that we had, where we said that we don't want to store any of the previous data samples. We want to store, let's say, a few examples from the previous tasks. Okay. And another alternative here is, instead of storing these examples from the previous task, we can also maybe produce these examples from a generative model. Okay. But then there are many questions on, how many more samples you want to store or generate. How do you select these samples, and then how exactly do you use them? So these are the questions that we will answer through a couple of methods. So the first one is that of ICAL, which is an incremental classifier and representation learning approach. So what this does is, this is a paper from 2017, CVPR, I believe. But again, you'll see the reference in my slides later. So here the idea is that we want to select samples for being stored as part of my, let's call it the memory of the old task, that are closest to the mean of each class. So you compute the features, you compute the mean of the feature of each of these classes, and then you select a few samples depending on the budget that you set, say 50 samples per class, and you collect these samples for these classes, okay? Or a total of, let's say, 2000. So you would get fewer and fewer samples as you get more and more classes per class, okay? And then you use the idea of knowledge distillation again to compute, the responses of the previous and the current classes. And then we will also use this memory, as I said, or the samples that we have selected from my previous classes or old tasks, let's say. So we'll see a bit in detail of this algorithm. So the first thing that is done here is, actually we are splitting the problem of classification into two, right? So I said there are two phases. The first one is where we compute the features, or learn to compute the features. And the second one is the classifier. And in this case, they're using a nearest class mean classifier, which means that you're kind of disconnected the feature representation and the classification part. And there is no training as such in this nearest mean classifier. It's like a nearest neighbor approach, where you just see which of the class means is closest to a sample, and then assign that sample to that class. So there is a question about what about long tail related to ICAL sample selection? Indeed, this would be a disadvantage, but each method has its pros and cons. If you don't have that many samples for a particular class, you would get a poor mean for that particular class, which means that nearest class mean classifier will not work great. And that is one of the disadvantages, or the cons, let's say, of this particular approach. Okay, so what we do overall is consider our input, which are the training examples, XS to XT of, let's say, our new classes. So these are our training examples that are given to us. And we also have a budget for the memory, which is defined by K. So you can store a total of K samples from your entire data set. Then what this requires is the theta, which are the current model parameters, and then also the current set of exemplars. Exemplars, represent the memory, or the samples from all the previous classes 1 through S-1 that you have stored. Okay. And each one here is, let's say, K divided by S-1 samples that exist in each of these exemplar sets. Okay, so the first step here is for us to update the representation by using the new data, the exemplar set, and the current set of parameters. Okay, and we'll see in detail what each of these kind of big steps involves, updating representation and so on. Then once we have updated the representation, which means retrained the feature part of my network, I will then update the number of exemplars I can store for each class, because now you have a new set of classes, which means the total number of samples, the number of samples for each class that you can store will reduce, okay? And that's exactly what is being done here. Is for each of my old classes, I'm reducing the exemplar set, and then for each of my new classes, I'm constructing an exemplar set, because I need to choose exemplars or samples from the new set of classes, okay? And given this, you have the entire set of new exemplars involving the old classes 1 to S-1 and the new classes S to T, okay? Right, I just went ahead in all of these explanations. Okay, so the next step, assuming you know how to do all of the previous steps, is to classify, where we simply look at, for each of the exemplar sets, I'm computing the mean given by mu y. Excuse me. And then I'm just assigning a sample from my training set to the one that is closest to the mean mu y, okay? And that y is my label for the test sample x, okay? Small x, let's say. Right, going ahead. So now the next step is, how do we actually do this update step, okay? And for doing this update step, we said we have data from the new classes, so data and the corresponding labels, right? We have the exemplar sets. There's a question, will you present an algorithm which is like iCal, but is considering? No, unfortunately not. But hopefully, there are some other methods that you can look up. But yeah, it is an important question, how to handle long tail distribution, but something that doesn't necessarily get handled by iCal as such. But then also, it can be a long tail distribution, but maybe, there are several things which are important here. Is the size of the memory. How many samples do you have initially for each of your classes, etc. So there are several things, even if it is long tail, and if you have sufficient number of samples, perhaps this method would not be so bad. Okay, so there's lots of ifs and buts. So given my new training data and my exemplar set, I would combine and form my entire training set of my new samples and my old samples, okay? And we also store the outputs of my old samples with respect to my old network, okay? And then you run the network training like a backprop algorithm with the loss function. And the loss function is composed of two parts. Sorry, I need to go down here. So, which is the standard, the cross entropy loss for learning the new tasks from S to T. And then you have like a distillation loss, which essentially compares the responses of my old samples from my old network with respect to the new network. Okay, so it's just a difference between them, and here you're looking at one type of distillation loss. That's what is being added. So here, the advantage with this method is that cleverly using the available memory, right? But then there are potential issues with kind of storing data. There is issues with privacy, because you are forced to store some samples, and there could be cases where you may not have access to these samples, you may not be able to store them, etc. Right? And another important thing is you're limited also by the memory capacity, right? Clearly, the more samples you want to store, the better. But then the more samples you store, the closer you come to actually increasing the size of your memory footprint for storing the previous samples. Okay, so that's iCal. So I'll quickly go through maybe one sort of generative model-based approach. You have seen generative models in this series of lectures that you've had in the summer school. So hopefully you'll be able to connect to that a little bit. So here I picked an example called Deep Generative Replay, which consists of a model which they call as Scholar, which is composed of two parts. One is a generator and then a solver, okay, a solver or a classifier, if you like, with respect to the image classification problem. And the generator and the solver, they are updated in every incremental step, right? So this is the entire model, and we update both of these in every step of the model, okay? And the training procedure involves these steps. At, let's say, a task T, what we do is we train a new Scholar by using not only the data that you have for that particular task T, so essentially the new task or new set of tasks, and you use all of them to learn the Scholar model or the new Scholar model. And in addition to that, we do not store any data from the previous Scholars, but we do have the Scholar that was trained for task until task T-1, right? So we use the Scholar to generate the data and then combine all of this data to update the Scholar. So maybe I'll go ahead a few steps, but just to kind of get maybe a little bit of feedback from you all. So in this particular framework, does anybody see an issue with this approach? What issues do you see with this approach, in particular with respect to generative model here? I can wait for a few seconds because I know there's a delay in getting the responses. So here is sort of the high level model that we are seeing, but does anybody see any disadvantages of this particular approach? Sort of greedy optimization, yes. Maybe I'll wait for a bit, I'll move on and I'll come back to it. What could be the issues with this? Okay, so the training procedure, right, has two steps. We need to train the generator and also the solver. So for training the generator, what we have is our current task, right, which includes the input and the label. We just use the current data X, and then we do a replay, essentially trigger the generator to generate all my data corresponding to the previous classes, and then use both of them together to solve or to update my generative model. Okay, so you retrain a new generator by using X and X prime, so old and new data together to create a generator, right? Already there is one thing that you may have noticed is that we're not using the labels Y in the generative model here. So right, potentially that is one issue. Then there is the second step of the training procedure, which is the solver, where you have data from task T, and you also get the data from the previous Scholar. So basically, you do the same thing as you did for the generator. You generate your data X prime using the generative model, but then you use the existing solver to also get the labels Y prime for this for these generated samples. Whereas in the case of current data, you will have the label automatically Y because it comes with the ground truth label. Now, using these two collections of data, X prime, along with their labels Y and Y prime respectively, we then learn the solver. Okay, so here again there is some issues, but let's see, there have been a few responses. We might slowly lose the influence of old Scholars. Indeed, absolutely. There is I think it also links to the greedy optimization approach, in that we kind of start forgetting what we had in the past, and there is a gradually fading effect, let's say, of the influence of the older classes, older Scholars, etc. May this also be subject to forgetting? Yes, so that's also a related answer. Data from older, not previous task, is gradually forgotten, so they're all related responses. And now there's a question, is it possible to update several classes rather than only one class in one update. Indeed, the framework does allow. I don't remember the full details of this particular work, but I think there is provision for doing this. I don't know if they experimented, but they do at some point talk about it. Combination of labels of different quality, weak and strong labels. Yes, so this is where I think you're hinting towards, the issues that I was talking about. So here we are generating samples, and here this is a class. It's not a class conditioned generator in this case, which means you will be generating labels, you will be generating data, but not necessarily representing the entire set of labels y prime, right? You're limited by what you generate, and then the solver only assigns a label based on what you've generated. So you might not necessarily generate a label generate a sample from all the classes, or at least there will be a huge potentially imbalance in this case. Okay. So to summarize the issues with this, the big advantage is that you're avoiding memory issues, because instead of storing a few samples or lots of parameters, a copy of the network, you're in this case, generating it on the fly, right? Which potentially can reduce the number of things that you need to store. But then, as some of you have already mentioned, there is an accumulation of errors as you start forgetting some of the older things. And also, as I said, there is no control over the class of the generated samples, right? So you might have a generator which is biased towards, let's say, one class, and you get lots and lots of samples from this particular class, and you have their corresponding label y prime, but maybe for the other y primes, you don't get as many samples, okay? So there are solutions that I think have been already proposed, and that you can make it, the generator maybe class conditioned, right? Something that you would have seen in these series of lectures in the summer school, and so on. Okay. Okay, so maybe very quickly, what I'll do is just at an even higher level, I'll talk about this third maybe class of approaches, and in particular, what is called as PACnet, right? So here, what is initially done in this framework is actually to kind of allocate the space of the parameters for different tasks, right? So here I'm showing, let's say, the weights from one layer of your deep learning model, right? And this is, let's say, the initial filter for when you've learned for one task, right? So it has some initialization, and then you train for task one, and then you get certain weights for these neurons within one layer, okay? And what is done in this PACnet approach is quite smart, is that you kind of say, okay, first I will prune all of these weights. I'll make sure that some of the weights are not used by this task. Okay, so there is some pruning of the weights, and then you retrain by kind of suppressing these neurons and allowing them not to change, so that they don't act for task one. Okay, and then now you move on to the next task, where you kind of fix the neurons which were learned for task one, the ones that you see here in gray. Okay, excuse me. And then you set up an initial filter for a new task, and then you train it. Okay, and then you get these weights that you have learned for task two, again, for only one layer and only few of the neurons from this layer. And then you do the same pruning step. Here maybe a little less dramatic pruning of, let's say, 33%, then you retrain it, and then you save only some of the weights that you have learned for task two, shown here in orange, and then you kind of switch off some of the others, okay? And you do the same thing for a task three. So you kind of keep going on and kind of making, using the space that you've allocated for different tasks as you go further along. So there are, clear advantages in that you have fixed memory consumption, right? And there is also evidence experimentally in this case to show that this kind of avoids forgetting. But there is a big constraint in that you really need to know the total number of tasks, right? And you need to know that because you need to have a model that has a capacity to kind of represent all of the tasks, because otherwise what would happen is you would make maybe too little space for some of the other tasks that are coming in the future, which means they won't be as well represented and you will not be able to learn. But then there are certain advantages of this method. Maybe you can kind of balance it out across the layers. Like for some layers, maybe the initial tasks play a heavy role, and for some of the others, maybe the ones that come later on maybe take a heavier role, right? So you can balance it perhaps across the layers. So there are some ways of mitigating these issues also, but again, no method is perfect. Okay, so in the maybe few minutes that are left, I just wanted to show very quickly, actually, these are not my results, but some interesting paper. I think that's now a PAMI paper now, but it's on archive since last year, where they kind of try to compare the different types of incremental learning approaches, right? And it's a topic that has kind of exploded over the last 4 or 5 years, and there's a lot of work that is being put into in this area, and there's many new methods. So this was one attempt at kind of comparing and analyzing different approaches, because there's a lot out there. And this was done on 2 data sets, TinyImageNet and iNaturalist, and they have different statistics in terms of roughly 8,000 training samples per task to going up to like 66,000 samples per task. So they're also different in terms of the validation set, and then also the number of classes is about 20 in ImageNet, and to roughly about 300 or more, in iNaturalist. Okay. Right, and here is just brief recap on the results on some of the methods. So the baseline that we saw, the naive solution 2, where you're fine-tuning the network, is the one shown here in black, and each column here represents a task. Okay, and there were 10 tasks, and each task was added at a particular point in time, right? And which means that task 1 has been seen. You can compute the performance on task 1 10 times because there are 10 tasks, whereas the performance on task 10 you only compute once because you had it was trained at the end. Okay, that's why there are more samples for task 1, and you'll see that fine-tuning, the performance is great in the beginning for task 1, but it jumps down immediately for as soon as you add task 2, and then it kind of never kind of recovers. And similarly for task 2, which comes in slightly later in time, initially it starts off great, fine-tuning, but then it drops. So the pattern kind of remains the same, right, across all the tasks. And one particular thing to note here is that of the memory-aware synapses method, the one shown here in red, which works pretty well, and so does PACnet in most cases. You'll see that these two are perhaps the top 2 performing approaches across all the tasks, more or less. Okay, and this is the other class of approaches, which is rehearsal and replay. In the previous graphs, we saw examples from regularization and architecture-based, so basically PACnet, and the others that we saw, like elastic weight consolidation, memory-aware synapses, learning without forgetting, etc. Okay, and then iCal, which has this memory, and other approaches are shown here. Okay, and you see here that maybe iCal with a higher amount of memory, which is 9K samples, performs clearly better than the orange curve with only 4.5K samples. Okay, right. So the general trends are that PACnet results in less forgetting, and it does produce some of the top results. And we see that memory-aware synapses is more robust than elastic weight consolidation. Okay, so what I'm going to do now is just go to maybe the summary slide, because we are pretty much out of time. Right, so maybe this, in that, from all this that we have seen, actually, is there a takeaway message we can say? Is that the larger models give more capacity. That's one problem with these approaches, but in that the larger the model, the better the performance is, and the better the capacity of the models to store more data in some sense. But this does lead to some overfitting. And it was also seen that the wider networks perform better than deep networks in terms of mitigating the effects of catastrophic forgetting. Again, all these are not justified in a theoretical sense. They're more sort of empirical observations that people have made. There is also other points to note in that the regularization clearly, right? So you have two terms in your loss function, and this may clearly interfere with incremental learning because you would want to perform well on the new classes, but if you put too strong regularization, you won't be able to change too many of the parameters. If you're using a model-based regularization, and this would not allow you to do well on the new classes. But again, it's a trade-off. And it has been shown that dropout actually can be used for handling this issue of weight decay. Right? How do you train these models with a weight decay? And dropout is something that has shown to perform well. So I won't have time to go through the other part that I was thinking of, but maybe I'll just summarize very quickly. And I see that there's already a few questions. I'll come back to that. So what have we seen in today's lecture is we have kind of seen sort of different flavors of approaches for incremental learning, right? I've only given you a few examples, and for details, you should definitely see the papers directly. But it will kind of give you the idea that there are different ways of handling incremental learning and the problems with dealing with catastrophic forgetting and everything. And clearly the problem is far from being solved. And there are more, let's say, stricter versions of incremental learning where, let's say, you just get new data, but it could correspond to either new classes or the old classes. In the framework that we have seen so far, we assume that the data always comes from a new class, which you haven't already seen. So even though it's not a strong information, it is an important enough information for us to handle. So there are some methods, notably, I think, at NeurIPS a couple of years ago, in what is being called as unsupervised incremental or continual learning. There are a few approaches for that. So that's, I think, clearly one way of going forward. So I'll take maybe a couple of questions from the chat, and then we'll see how to end. Right. Oops. So just a second, I lost my chat. Okay. So do you think do you think that the results are applicable to other domains which are beyond the classification? Indeed. So I didn't have time to go through one, but there is classification, but you can also do the same for the detection problem that I was mentioning. There is some work that started looking at how you would do it for image segmentation. There is also work away from, let's say, the computer vision domain in terms of handling, time series data, where clearly you have, data coming in at different points in time. So there is other domains also. There are other domains which do look at it. The next point is, I feel there might be a connection to learn models with missing data. Right, indeed, the problem of missing data is a very, very important question. I'm not sure, you maybe have seen some lectures already. So yes, so we do there are some papers making this link. I don't know any off the top of my head, but making link between missing data and this incremental learning. So you can see it that way, but it's an important point. I don't know how you would solve it, but I think there is an important link that can be made there. Oh yeah, the paper, name of the paper for the detection task. So here I'm going to be doing some self-promotion, I suppose. Actually, it's more a promotion of my former student, Konstantin, who did this paper at ICCV 2017, which is called Incremental Learning of Object Detectors. So this was one paper, and there are a few follow-up works that have come up from here, which I haven't followed up so much the literature on detection, but there are approaches. So if you see this paper as a starting point and then see the references, the papers that cited, you will see more newer methods. So this is one example of detection. Okay, so I think I've taken all the questions on the chat. And yes, please.
Yes, I think you already take all the question on the chat. And I think due to time limitation, because it's already running out of the time, so we have to start at here. So let's thank Karteek to give us an excellent lecture about incremental learning. Thank you very much. Thank you.
Thank you. Thank you again for the invitation, and well, hopefully see you in person sometime soon.
Yes.
Yes. Have a good evening then, everyone. Thank you all.
Thank you. Thank you.
Bye.
Bye bye. Are we still online?